Introduction to Azure Load Balancer. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into Azure Load Balancer, one of the fundamental networking services in Azure. If you're building applications in Azure, understanding Load Balancer is absolutely essential for creating highly available and scalable solutions. Azure Load Balancer operates at Layer 4 of the OSI model. That's the transport layer. This means it works with TCP and UDP traffic, making decisions based on IP addresses and port numbers rather than looking inside the application data itself. Think of it as a traffic director that sits in front of your virtual machines or other resources, intelligently distributing incoming requests to ensure no single server gets overwhelmed. What makes Azure Load Balancer particularly powerful is its deep integration with the Azure platform. It's not just about distributing traffic, it's about doing so in a way that's highly available, scalable, and secure. Throughout this presentation, I'll show you exactly how to leverage these capabilities for your own application. Core Components Overview. Let me walk you through the 5 essential components that make up an Azure Load Balancer. Understanding these building blocks is crucial because they work together to create a complete load balancing solution. First, we have the front-end IP configuration. This is the entry point for all traffic, the IP address that your users or applications connect to. In this diagram, you can see it's represented as a public IP address receiving traffic from the internet. However, it's important to note that this could also be a private IP address for internal load balancing scenarios. The load balancing rule is where the magic happens. This rule defines how traffic should be distributed. In our example, it's taking traffic coming in on TCP port 80 and distributing it across the backend pool on port 80. You can have multiple rules on a single load balancer, each handling different ports or protocols. The backend pool consists of your actual workload, typically virtual machines or VM scale set instances. These are the resources that will actually process the requests. Notice how the load balancer distributes traffic across all 3 virtual machines in our example. Health probes are your safety net. They continuously check each backend instance to ensure it's healthy and capable of handling traffic. If a probe fails, maybe because a web service crashed or a VM is undergoing maintenance, the load balancer automatically stops sending traffic to that instance until it recovers. Finally, inbound NAT rules provide direct access to specific backend instances. In the diagram, you can see how an RDP request gets forwarded directly to VM1. This is incredibly useful for management scenarios where you need to connect to a specific VM without exposing each versus M's public IP address. Requirements mapping high availability. Let's talk about one of the most common requirements I see in production environments: the need for high availability and fault tolerance. This is where Azure Load Balancer really shines. The combination of health probes and backend pools creates a self-healing system. Here's how it works in practice. Let's say you have 3 web servers in your backend pool, and one of them experiences a failure. Maybe the IIS service crashes or the virtual machine itself has an issue. The health probe, which might be checking port 80 every 5 seconds, will detect this failure within seconds. Once the probe fails a configurable number of times, the default is 2 consecutive failures. The load balancer marks that instance as unhealthy and immediately stops routing new connections to it. Existing connections might still complete, but no new traffic goes to the failed server. This happens automatically without any manual intervention. For maximum fault tolerance, you should combine this with Azure's infrastructure features. Place your virtual machines in an availability set to ensure they're distributed across different fault domains and update domains. Or better yet, if you're using the standard SKU, spread them across availability zones. This protects you not just from individual virtual machine failures, but from entire data center level issues. I've seen this save production deployments countless times. One client had a memory leak in their application that would cause crashes after several hours of runtime. While they worked on fixing the root cause, the load balancer's health probes ensured that users never experienced downtime. Failed instances were automatically removed from rotation, and new traffic was seamlessly redirected to healthy servers. Public versus internal load balancers. One of the first decisions you'll make when creating a load balancer is whether it should be public-facing or internal. This choice fundamentally changes how your application architecture works. A public load balancer gets a public IP address as its front end. This makes it accessible from the internet, which is perfect for web applications, APIs, or any service that needs to be reached by external users. The beauty of this approach is that your backend virtual machines don't need public IP addresses. They can use private IPs only, which is more secure and cost-effective. All internet traffic flows through the load balancer, which acts as a single point of entry. On the other hand, an internal load balancer uses a private IP address from your virtual network. This is ideal for multi-tier applications where you want to distribute traffic between tiers without exposing them to the internet. For example, your web tier might need to communicate with an application tier, which in turn talks to a database tier. Internal load balancers keep this traffic within your virtual network, maintaining security while still providing load distribution and high availability. Here's a real-world example. I worked with a financial services company that had a 3-tier application. They used a public load balancer for their web tier to serve customer traffic from the internet. But between their web tier and application tier, they used an internal load balancer. This ensured that their business logic layer was never directly exposed to the internet, while still benefiting from load balancing for scalability and availability. The commands shown here demonstrate creating both types. Notice how the only real difference in the Azure CLI is whether you attach a public IP or configure a private front-end IP configuration. The core functionality remains the same. Inbound NAT rules explained. Inbound NAT rules are one of those features that might seem minor at first, but become invaluable in practice. Let me explain why they're so useful. Unlike load balancing rules that distribute traffic across multiple backends, NAT rules create a one-to-one mapping. They forward traffic from a specific port on the load balancer's front end to a specific port on a single backend instance. This gives you direct, predictable access to individual virtual machines. The most common use case is management access. Imagine you have 10 web servers behind a load balancer. They all have private IPs for security, but occasionally you need to RDP or SSH into a specific server for troubleshooting. Without NAT rules, you'd need to either give each virtual machine a public IP, expensive and less secure, or set up a jump box, which adds complexity. With NAT rules, you can map different ports on the load balancer to different virtual machines. For example, port 50001 on the load balancer forwards to virtual machine 1's RDP port 3389. Port 50002 forwards to virtual machine 2's RDP port, and so on. You get direct access to each virtual machine through a single public IP. The Azure CLI command shown here creates exactly this scenario. The front-end port 50001 parameter specifies the port users will connect to on the load balancer, while back-end port 3389 is the actual RDP port on the virtual machine. The back-end pool member parameter identifies which specific virtual machine should receive this traffic. I've also seen creative uses beyond management. One customer used NAT rules to provide direct access to specific application instances for debugging, allowing developers to connect directly to a problematic instance while normal user traffic continued to be load balanced. Outbound connectivity patterns. Outbound connectivity is often overlooked when designing Azure architectures, but it's crucial for real-world applications. Your virtual machines need to reach out to the internet for various reasons, such as downloading updates, calling external APIs, or sending telemetry data. When you place virtual machines in the backend pool of a public load balancer, Azure automatically configures Source Network Address Translation, or SNAT. Here's what happens. When a backend virtual machine initiates an outbound connection, its private IP address is translated to the load balancer's public IP address. From the Internet's perspective, all traffic appears to come from the load balancer. This automatic SNAT is convenient, but it comes with limitations. Each virtual machine gets an allocation of SNAT ports, also called ephemeral ports, and if your application makes many outbound connections, you can exhaust these ports. This leads to connection failures that can be hard to diagnose. The diagram shows the complete flow. Traffic originates from virtual machines with private IPs, gets translated by the load balancer, and appears on the Internet with the load balancer's public IP. The return traffic follows the reverse path, with the load balancer maintaining the connection state. For production workloads, I strongly recommend using Azure NAT Gateway instead of relying on Load Balancer SNAT. NAT Gateway provides dedicated outbound connectivity with predictable SNAT port allocation and better scalability. You can see in the warning box that this is now the recommended best practice. The command shown creates an outbound rule, giving you more control over SNAT behavior, including the ability to use multiple public IPs to increase available SNAT ports. Multi-tier application architecture. Let's explore how load balancers fit into complex, multi-tier applications. This is where the real power of combining public and internal load balancers becomes apparent. In this architecture, we have 3 distinct tiers, each with its own load balancer. The web tier uses a public load balancer to receive traffic from Internet users. These web servers then need to communicate with the application tier for business logic processing. Instead of having each web server track which app servers are available, they simply send requests to an internal load balancer. This internal load balancer for the app tier provides several benefits. First, it abstracts the app tier infrastructure. Web servers don't need to know how many app servers exist or their IP addresses. Second, it provides automatic failover. If an app server fails, traffic automatically routes to healthy instances. Third, it enables independent scaling. You can add or remove app servers without updating web server configurations. The pattern continues with the database tier. While you might think databases don't need load balancing, consider scenarios like SQL Server always-on availability groups or read replicas. The load balancer can direct traffic to the active primary node or distribute read queries across multiple replicas. The Azure CLI commands here show creating an internal load balancer with a private front-end IP from your subnet. The private IP address parameter lets you specify a static IP that your other tiers can reliably reference. Notice how we're using the same health probe and rule configuration. The only difference is the front-end IP type. I implemented this pattern for an e-commerce platform that needed to handle Black Friday traffic. The ability to independently scale each tier while maintaining high availability was crucial for handling the 10x traffic spike. Basic versus Standard SKU Deep Dive. Choosing between Basic and Standard SKU is one of the most important decisions you will make, and I want to be very clear. Standard SKU should be your default choice for any production workload. Let me explain why by walking through this comparison table. The most critical difference is the SLA. Basic SKU has no SLA, none at all. If there is an Azure platform issue affecting your basic load balancer, you have no recourse. Standard SKU provides a 99.99% SLA, which translates to less than 53 minutes of downtime per year. For business-critical applications, this alone justifies using standard. Scale limits are another major differentiator. Basic supports up to 300 backend instances, which might seem like a lot until your application grows. Standard supports up to 5,000 instances. But it is not just about numbers. Standard allows any virtual machine in your virtual network to be a backend pool member, while Basic restricts you to virtual machines in a single availability set or scale set. This flexibility is invaluable for complex architectures. Security is where I see the most impactful difference in practice. Basic SKU is open by default. Any traffic that reaches it will be forwarded unless you explicitly block it with NSGs. Standard SKU flips this model. It is secure by default, denying all traffic unless you explicitly allow it with NSG rules. This deny by default approach aligns with security best practices and has prevented numerous security incidents. The diagnostic capabilities of standard SKU have saved me countless hours of troubleshooting. While Basic only integrates with log analytics, Standard provides rich multi-dimensional metrics in Azure Monitor. You can see real-time data about connection counts, SNAT port usage, health probe status, and more. These metrics are invaluable when diagnosing performance issues or planning capacity. Availability zones and regional versus global tiers. Let's talk about achieving extreme high availability with availability zones, and the choice between regional and global tiers. This is where Azure Load Balancer really shines for mission-critical applications. Availability zones are physically separate data centers within an Azure region. Each zone has independent power, cooling, and networking. When you deploy a zone redundant standard load balancer, Azure automatically replicates it across all zones in the region. If an entire data center fails, your load balancer continues operating from the other zones without any action from you. The regional tier is what most applications use. Your load balancer and all backend resources exist within a single Azure region. With standard SKU, you can make this zone redundant for protection against zone failures. This setup handles 99.99% of high availability requirements. The global tier, available only for public standard load balancers, takes this further by enabling cross-region load balancing. Imagine you have applications deployed in East US, West Europe, and Southeast Asia. A global load balancer can distribute traffic across all these regions, providing protection against entire region failures. The diagram shows this clearly. The global load balancer sits above regional deployments, each with their own regional load balancers. If the East US region becomes unavailable, traffic automatically shifts to the remaining regions. This is different from Azure Front Door, which does geographic routing based on user proximity. Global Load Balancer is purely about availability, not performance optimization. The CLI commands demonstrate creating both types. Notice the tier parameter and how we specify zone redundancy with the zone parameter. For global tier, you also need to configure region-specific backend pools, which involves additional commands to map regions to the global front-end. Practical implementation example. Let me walk you through a complete, real-world implementation of a standard public load balancer. I'll explain each command and parameter so you understand not just what to do, but why. First, we create the foundational resources, a resource group and virtual network. The VNet needs at least one subnet where your backend virtual machines will live. Notice I'm using East US, but choose the region closest to your users. Next, we create the public IP for our load balancer. The SKU standard parameter is crucial here. A standard load balancer requires a standard SKU public IP they must match. This public IP will be the single point of entry for all internet traffic to your application. Creating the load balancer itself requires several parameters. The SKU standard gives us all the advanced features we discussed. The public IP address associates our public IP. The front-end IP name and back-end pool name create named configurations we'll reference later. The health probe is your application's heartbeat monitor. This TCP probe on port 80 checks if your web servers are responding. By default, it probes every 5 seconds and marks an instance as unhealthy after 2 consecutive failures. You can customize these thresholds based on your application's characteristics. The load balancing rule ties everything together. It says take traffic arriving at the front end on port 80 and distribute it to the backend pool on port 80, but only to instances that pass the health probe. This is a simple example. You can create multiple rules for different ports and protocols. Finally, we add virtual machines to the backend pool by updating their network interfaces. This is done at the NIC level, not the virtual machine level, which allows for more flexibility. Each virtual machine can be part of multiple backend pools if needed. Thank you for your attendance. Please consider subscribing to the channel.